Hello class! 13.3 is on geometric sequences and series. A geometric sequence is a sequence with a pattern of multiplication by a constant number, called the common ratio, in order to move from term to term. Given the general geometric sequence below, complete the table that follows. Okay, so every geometric sequence begins with a first term. We'll just call that A. And then to go from term to term, we multiply by a common number called the ratio. We'll use R to represent that. So I multiply by R to go from the first term to the second term, and I get A times R. But then I continue that pattern, multiply by R again. So if I take AR and multiply by R, I get AR squared. And you can see this pattern continues, and the net effect is just that the exponent on the R keeps increasing by 1 as I continue to multiply by R to go from term to term. And furthermore, we'll say that A without a subscript stands for A sub 1, the first term. A times R will therefore be our second term. AR squared will be our third term. AR to the third will be our fourth term. And AR to the fourth will be our fifth term, etc. So the first thing we want to do is establish an explicit formula for such a sequence. Notice that, looking at this pairing here, the number term I'm on, if you remove 1 from that number, you get the correct exponent on the ratio. So in other words, if we're on the fifth term, then there should be a 4 exponent here on that ratio. And that's consistent across the board, telling me that I can create a general explicit formula by saying the following, that the nth term of the geometric sequence will be equal to the first term, A, times the ratio, but raised to one number less than the term that we're on. So A times R raised to the n minus 1. And this will produce all of the terms of a geometric sequence, provided you know what the first term is and you know what the ratio is. And a recursive formula. Well, to go from term to term, we simply multiply the prior term by R to get the next term. So we have A sub n is equal to R times the prior term, which is A sub n minus 1. And of course, we need to specify what the first term is. It's A. You can also write this in the following way. A sub n plus 1 is equal to R times the previous term, which in this case would be A sub n. So both of these are saying the same thing. They establish the same relationship, and in both cases, A sub 1 is just A. Now we're going to establish a formula for the sum of the first n terms. Well, let's give a symbol for the sum of the first n terms. I'll do S sub n, meaning the sum of the first n terms. And it's going to be A plus AR squared, etc., until we get to the nth term, which will be AR to the n minus 1. That is the explicit formula for finding the nth term of our geometric sequence. Now, if I multiply everything in this by R, so we have R times S sub n, we get the following, AR plus, and we distribute the R across all these terms. So the power in all the R's is just going to go up by 1. So we get AR squared for the second term here, AR cubed, etc., up until, and the last one will be AR to the n. We increase the power by 1. Now, these two sums have a lot of terms in common. All those terms there are in common. So if I subtract the two equations, I get the following. S sub n minus R times S sub n is equal to, and then let's identify what's going to cancel. Those are going to cancel, because we'll do AR minus AR. AR squares will cancel, AR cubes will cancel, and that pairing will cancel. The only things that won't cancel is what is not currently highlighted. So we're going to get this A right here, and then minus, and then this term over here. Now if I factor out S sub n from the left side of our equation, and I factor out A from the right side of our equation, and then do some division, we can find a formula for S sub n, the sum of the first n terms. And we get A times 1 minus R to the n over 1 minus R. This is the formula we're going to use for the sum of the first n terms of a geometric sequence. So it's going to be the first term times 1 minus R raised to the n, where n is the number of terms, and R is the ratio, and A is the first term, and then divide by 1 minus the ratio. An alternate way, if you multiply the top and bottom by a negative 1 and distribute the negative 1 across the differences, you could also write it this way. A times R to the n minus 1 divided by R minus 1. So just switch the subtraction orders of both the top and the bottom. Either one of those will be acceptable. Now, for the geometric sequence below, determine 1, the common ratio, 2, an explicit formula, 3, a recursive formula, 4, the 8th term, and 5, the sum of the first 8 terms. All right, so the common ratio will be the number that we multiply to go from term to term. And you can see that we are multiplying by a negative 2. That is not x minus 2, by the way. That's times a negative 2. And that is consistent to go from term to term. We keep multiplying by a negative 2. So notice that if you have a negative ratio, then your geometric sequence will be alternating in the sign. It will be plus, minus, etc. Because as you continue to multiply by that negative number, you just keep changing the sign. And so let's go ahead and write down what our ratio is. This will be step 1. The ratio is negative 2, so r is negative 2 here. We also can identify the first term. We'll go ahead and write that down, even though it wasn't asked. The first term is 3, so a is 3 and ratio is negative 2. And we want to now come up with question 2, an explicit formula. So question 2, an explicit formula, we can borrow what we see right here and just replace a with 3 and r with negative 2. So our explicit formula is a sub n is equal to a, which is 3, times r to the n minus 1. And this will produce all the terms of your geometric sequence. Now, with a little bit of exponential or exponent manipulation, we can also rewrite it this way. 3 times negative 2 to the n times negative 2 to the minus 1. We break apart this n minus 1 as n plus negative 1, and then break up the exponent on each exponent on its own base. And then we could, negative 2 to the negative 1 is just negative 1/2, and then multiply with that 3 in the front. We can write this as negative 3/2 times negative 2 to the n. This is also an acceptable general formula for the explicit general formula for the nth term. But we can also just stick with this one. Number 3, find a recursive formula. A recursive formula would simply be that a sub n plus 1 is equal to negative 2 times a sub n. So to go from term to term, you just multiply by negative 2. So a sub n plus 1 is the term after a sub n, so you take the prior term, multiply it by negative 2, and that's how you get the next term. But we also need to specify what the initial term is. So we'll say with the first term, with a sub 1 being 3, or you can just say a equals 3. If you see a without a subscript, assume it means the first term, unless otherwise indicated. Number 4, find the 8th term. Well, we can use the explicit formula above to find the 8th term. A sub 8 will be equal to 3 times negative 2 to the 7th power. So I'm just using this formula right here, but changing the n to 8. And we can get the 8th term. And whether or not you simplify this, it will depend on how large these numbers are. Of course, you can reach for a calculator. I know that 2 to the 5th is 32, so 2 to the 6th is 64, and 2 to the 7th is 128. And a negative number to the 7th will stay negative. So we have 128, and then we're going to triple that, and so we should get a negative number here. We're going to do 3 times 128, and 3 times 128, we get negative 384. Now, another way you could have found the 8th term, of course, would have been to just continue the pattern. We have the first 4 terms already, so you just have to multiply negative 24 by negative 2, we get 48, and then negative 2 times that will give you negative 96. Negative 2 times that will give us 192, and then negative 2 times that will give us the negative 384. So we could also just continue that way. And finally, the sum of the first 8 terms. All right, so the first term is 3, and then we're going to subtract 8, and then we're going to subtract 6, then add 12, then subtract 24, and we're going to continue this up until we get to the 8th term, which is subtracting 384. And you could, since there's only 8 terms here, you could just go ahead and combine all these together and then get an answer, but let's use the formula that we just devised up here to get the answer. So according to our formula, we're going to use, typically when my ratio is more than, well, depending on what the signs of the numbers are going to be, I will use either this formula or this formula, whichever one avoids the most negatives. And so since my ratio is negative, I realize that if I use this denominator here, I'll have a 1 minus a negative number. That'll be a positive denominator. Or over here, I'll have a negative denominator. So I'm just going to go ahead and use this version of our formula. It really doesn't matter, though. They should simplify to the same thing. And so we get a, which is the first term, which is 3, times 1 minus the ratio, which is negative 2, and that's raised to the number of terms. The number of terms is 8. And be mindful, when I find the 8th term, I have a 7 as an exponent, but when I find the sum of the first 8 terms, there's an 8 back as an exponent on the negative 2. This change is often a source of error for students. And then, of course, we divide this by 1 minus, and then just negative 2. Now, 1 minus negative 2, this is going to be a 3. That's going to cancel with that 3, so those will just become 1. And we just have to now do this calculation. And negative 2 to the 8th is equal to, don't forget to do the 8th power on the negative first, and then see whether the subtraction will remain or whether this will become addition. But negative 2 to the 8th power is going to go positive. And 2 to the 7th was 128, so 2 to the 8th is 256. So that's going to be, what I have circled right now will be a positive 256, and we do 1 minus that. So you have 1 minus 256, and that's going to give us negative 255. I'll leave it to you to verify that that is the sum of the first 8 terms of this geometric sequence. Okay, let's go to the next slide. A geometric sequence has the indicated terms. Find the following: the 10th term and the sum of the first 10 terms. Now, this particular geometric sequence, we have the 4th term and 8th term presented, so we have to do some detective work to figure out what the common ratio is and see if we can figure out what the first term is. And there's a few ways to do this. One is to start writing out blank spots for the terms. So here's the first term, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, and 10th term. Now, which of these terms do I know? I know the 4th term is a quarter. And I know the 8th term over here is 64. And I also know that to go from term to term, I multiply by whatever the ratio is. So we've got to figure out how many steps that is. 1, 2, 3, 4 steps to get to this position. To go from the 4th to the 8th position, we multiply by r 4 times. So this tells me that 1/4 times the ratio to the 4th should give me the 64. And now we just have to figure out what r is. And solving for r, we get r to the 4th is equal to, let's go ahead and multiply 4 times 64. That's going to be 256. And then we want to do the 4th root of that next. When you do an even root, we get multiple answers. So we get plus or minus here, which opens up the possibility that there could be multiple answers to this scenario. So you have plus or minus the 4th root of 256. So we need a number that when you raise it to the 4th power, you get 256. It turns out that that number is 4. And so we have plus or minus 4 could be the ratio. So there's going to be 2 different possible answers here. So I'm going to copy this. I'll put one answer up there above, and I'll put the other answer down here below. If the ratio is positive 4, let's go with positive 4 as a possible answer. So that means, let me write down here, we're going to multiply by 4 to go from that term to the next term. Let me move this down slightly. And 4 times positive 4 takes you to 1. And 1 times 4 is 4, and 4 times 4 is 16. And sure enough, 16 times 4 is 64. And 64 times 4 is 256. And then the 10th term will be 4 times 256. Well, 4 250s is 1,000, and 4 6s is 24, so we should get 1,024. Now, going the other direction, if going from left to right you multiply by 4, then going right to left you divide by 4, or you multiply by its reciprocal. So I'm going to go this direction, we divide by 4. So if we're at 1/4 and I go to the left 1, divide by 4, that should take me to 1/16. Divide that by 4 should take me to 1/64, and divide that by 4 should take me to 1/256. So here is our geometric sequence. Now the other option was we multiply by a negative 4 in one direction, so the other direction will be divide by negative 4. So 1/4 times negative 4 is negative 1. Negative 1 times negative 4 goes back to positive 4. 4 times negative 4 is negative 16, and sure enough, negative 16 times negative 4 takes us to 64. And then we get negative 256 next, and then after that we have positive 1,024. Going the other direction, 1/4 divided by negative 4 is negative 1/16. Negative 1/16 divided by negative 4 is positive 1/64. And 1/64 divided by negative 4 is negative 1/256. So the only difference between these two possible answers is that one is alternating signs and the other one is not. But they both produce the same 4th and 8th numbers, which are 1/4 and 64. Now another way to have done this is to use the explicit formula for both of these bits of information and to solve a system for a and r. For example, a sub 4, according to the explicit formula, would be the first term times ratio to the 3rd power. We want that to be a quarter. And the 8th term, according to the explicit formula, would be the first term times r to the 7th, and we want that to be 64. Now what we do is we divide the two equations. So we're going to take the AR to the 7th and divide it by AR cubed, which means we should get 64 divided by a quarter. Notice that this leads to a cancellation of the A's. They'll cancel. And then the R to the 7th divided by R cubed is R to the 4th. And R to the 4th is equal to, and then 64 divided by a quarter is going to be our 256. And then we get our same R we got before, plus or minus 4. And then of course, once you know R, you can go back to either one of these equations, plug in that correct R and solve for A. And you're going to get two different A's depending on which R you started with. In one case, you're going to get A is positive 1 over 256, and in the other case, you're going to get A is negative 1 over 256. So this is just an alternate way to go about finding A and R. Now we want to find the sum of the first 10 terms. So we have to use the formula for finding the sum twice, once for each possible sequence. So in case 1, and I should specify right here, here's our 10th term in each case. In each case, the 10th term is a positive answer. It's 1024. So question 1 will have only one answer. Case 1 is that the first term is 1 over 256, and the ratio is positive 4. And in such a case, we know that the 10th term, and we could use the formula now, but we don't need to since we already found it. But it would be, so let me go ahead and write this down. It's A, 1 256 times R, which is 4 to the 9th power. And when you calculate this, you should get the 1024. And then the sum of the first 10 terms. So if we take the first term plus up to the 10th term, we can abbreviate that with a symbol called S sub 10. This means the sum of the first 10 terms. So the sum of the first 10 terms will be the first term, it's going to be A, times, now my R is 4, so I'm going to go with the expression that has R as first. So I'm going to go R to the 4th minus 1 over R minus 1. Here's our formula for finding the sum of the first 10 terms. And I need to change that 4 to a 10. That was a mistake on my part. The N is the number of terms, and the R's will be 4's. And the A is this fraction, 1 over 256. So we get 1 over 256 times R is 4, so we have 4 to the 10th minus 1, and then on the bottom we have 4 minus 1. And this gives us an answer of 4 to the 10 minus 1 in the numerator, and the denominator is 3 times 256, 768. And then if we reach for a calculator, we want to do 4 to the 10th minus 1 over 768. So I do 4 raised to the 10th, it's a large number, then minus 1, and then divide that by 768. And Desmos gives us an answer in decimal form, but if you click this little symbol over there, it'll give you the answer in fraction form. So 349,525 over 256. So that was case 1. And in case 2, we have the first term is negative 1 over 256, and the ratio was negative 4. Was another possibility. And in such a case, we have the 10th term, so A sub 10 will be the first term, which is negative 1 over 256, times the ratio to the, and the ratio is negative 4, so let me put a negative 4 in here and use parentheses, raised to the 9th power, one number less than the term we're looking for. And we've already done this work here. We're still going to get a positive 1024, should be the result of this calculation. Right, that work was already done over here. And then the sum of the first 10 terms, S sub 10, will be equal to the first term A, so negative 1 over 256, times the ratio. This time I'm going to go with the version of the formula where I have the R's, the R's are second in the differences there. Just because my ratio is a negative number now, so I'm going to switch that around. So we multiply this by 1 minus the ratio, which is negative 4 to the 10th power, divided by 1 minus the ratio, which is negative 4. So this gives me, we have a 5 down there, so we have to do 5 times 256. So we're going to get a 1280 denominator. And then the numerator, we have negative 4 to the 10th. That's going to be the same thing as just 4 to the 10th. This negative right here will disappear. It has no effect. So we have a 1 minus 4 to the 10th. But then we have this negative here in front. If I distribute that, we'll get 4 to the 10th minus 1. So we get this result. Notice right away when I compare the two, they look pretty similar when you compare these two structures right here, except the one on the bottom is dividing by a larger number. So the sum on the bottom should be a smaller number, which makes sense because when you add some positives and some negatives, you get cancellation happening. And let's go ahead and reach for the calculator. 4 to the 10th minus 1 over 1280. There we go, divided by 1280. Gives me 209,715 over 256. We do get a smaller number than we got before because of that negatives will cancel some of the positives when you add them together. And let's go ahead and look at what the decimal version of this is. It's about 819.2, we'll say. Approximately 819.2. That should be a sensible answer. All these numbers here early in our sum are so small as to be negligible. And then we have an 1,000 here, but remove a 256, but put a 64 back, remove a 16, add a 4. So we do expect a number that is less than 1,000 overall, and we're getting a number that's 819.2 when you add these all together. Okay, let's move to the next slide. A geometric sequence has the indicated terms. Find the following. So this is a similar question, but we're going from A4 to A7, and we're going from 48 to 6. Let's do the process where I just create a system of equations and solve it. So we know that A sub 7, according to the explicit general formula, should give me A times R to the 6th power, and we want that to be a 6. Whereas A sub 4 is going to be A times R to the 3rd power, and we want that to give me a 48. So I'm going to divide the two equations. And so we have AR to the 6th divided by AR cubed, and that should be equal to 6 divided by 48. The left side, the A's cancel. R to the 6th over R cubed is just R cubed. And over here on the right side, we get 1/8. And this time we're doing a cube root. And when you do a cube root, you don't get plus or minus. So we just do the cube root of 1/8, and that's going to be 1/2. So our ratio was 1/2, which makes sense. If you take 48, and to get from the 4th to the 7th term, we need to multiply 48 by 3 r's, or multiply by r 3 times, I should say. So 48 times 1/2 is 24, 24 times 1/2 is 12, and 12 times 1/2 will get me to the 1/6. So we continue to multiply by 1/2. Negative 1/2 would not work here, because that would take me to -6, not +6. So only one value of r is acceptable in this case. And since r is 1/2, we want to plug r equals 1/2 into either of these equations. I'll use the one I'm circling right now. And so we have a times 1/2 cubed is equal to 48. So that's a times 1/8 is equal to 48. And then multiply both sides by 8, and we get our first term, which is what we need to know. And 8 times 48, 384. Okay, now we can go back and answer these questions. The 10th term. We know our general formula. So a sub n is equal to the first term, which we just found is 384, times the ratio, which is 1/2, raised to the n minus 1 power. This is our general formula for the nth term, our explicit formula. Now, to find the 10th term, we would simply say a sub 10, therefore, is equal to 384 times 1/2 to the 9th power. And I'm not going to simplify this all the way, so let's just leave our answer as 384 over 2 to the 9th is one way to write this. Second question, our 20th term would be 384, the first term, times 1/2 to the 19th power. So we get 384 times, or divided by 2 to the 19th. Now, which of these is smaller? Well, keep in mind that to go from term to term, we're multiplying by 1/2. So to go from the 10th term to the 20th term, we did a lot of multiplications with 1/2. So we kept shrinking the number. So this number right here should be a lot smaller than this number here. And that's true because they have the same numerator, but this one here has a larger denominator. So 2 to the 19th is much larger than 2 to the 9th. And therefore, this fraction is much smaller than this fraction. Now we want to do the sum of the first 10 terms. So the sum of the first 10 terms is going to be equal to the first term, which is 384, times, and since the ratio is 1/2, I'm going to go with the version of the formula where r comes second in the subtraction. So we're going to have times 1 minus the ratio to the 10th power divided by 1 minus the ratio. And 1 minus the ratio is 1/2. And so if I do 384 divided by 1/2, that just winds up doubling 384. So I won't take this much further, but it looks like this. Doubling 384 gives me 768. And 768 times 1 minus, and then 1/2 to the 10th power will just be 1 over 2 to the 10th power. So I want you to observe something, that this answer is extremely close to 768 because 1 over 2 to the 10th is extremely small. So this is practically 0 here, and 1 minus it, therefore this is practically 1. And a number that's very close to 1, but less than 1, times 768 will give us a number very close to, but lower than 768. So this is below 768, but not far from 768. Keep that in mind. Number 4, the sum of the first 20 terms. The sum of the first 20 terms, according to the formula, is 384. It's going to be the same thing we just wrote above, except that we're going to have a 20 exponent on that 1/2. So we're going to get a lot of similar results. We're going to get 768 times 1 minus 1 over 2 to the 20th power. This answer, notice right here, this is even closer to 0 than the prior fraction up above. So this is even closer to 1 than this expression. So this answer is even closer to 768 than this answer. But they're both below it. And number 5, the sum of the first. Let me write our sum this way using sum notation. But this, we're going to be finding the sum of the first 50 terms. Using sigma notation, all you have to do is put the explicit formula in as your summand. So 384 times 1/2 to the n minus 1. And we're going to go from n equals 1 to 50. And this will give you those 50 terms. If you start with an index of 1 and end on 50, that does represent 50 terms. And this gives you all the different terms we need to add together. So this is what your sum would look like using summation notation. And we can already see that the answer is going to be 768 times 1 minus 1 over 2 to the 50th. Right, using the formula here in the same pattern we've done before to get this similar result. So we should get an answer that's even closer to 768 than before, because this is so extremely small. It's practically 0. 1 minus it is effectively 1, but slightly less than 1. And then multiply that by 768, and we should get a number extremely close to 768. In fact, all of these should be pretty close to 768. Let's go ahead and reach for the technology to confirm this. Let's do the last one first using technology. So back to Desmos. You can just type in the word sum, S-U-M, and it'll make a summation notation. We'll go from n equals 1 up to n equals 50. And we had a 384 times a 1/2. And that needs to be raised to the, you can use N, K, I, whatever letter you put in the bottom left as the index of summation. Just make sure you use that letter as well. And our exponent is going to be an n minus 1. So I'm going to use parentheses for that. Make sure we can type in n minus 1. Okay, now notice that Desmos is giving us an answer that's effectively 768. This is not a correct. Desmos is giving us a rounded answer because the answer is so close to 768 that the number of digits it rounds to, it's effectively 768. Now, if we were to change our upper number here and do the sum of the first 10 terms, notice what we get is an answer, 767.25. So let's go ahead and type that in, or enter that in our work over here, these answers. So the sum of the first 10 terms right here turned out to be 767.25. So look how close we already are to 768. When I do the first 20 terms, I can just change this upper limit here to 20. And notice how close we are, where it's 7, I'm going to do some rounding here, so about 767.9993. 767.9993. And then the sum of the first 50 terms is, according to Desmos, because of the rounding, it's just giving us 768. But in reality, it's not quite 768. It's extremely close, though. It probably has a 767 point and then several nines. So it's effectively 768 at this point, which is interesting. It seems like the more and more terms we add together, the closer our answer gets to 768, which might make you think that if we added up a trillion terms, we would effectively have 768. If we added up a trillion terms, if we added up all of the terms, infinitely many, would we have 768? Interesting question. Let's explore this idea of infinite sums here. A geometric series is the sum of all the terms of a geometric sequence, provided this is possible. So here we have summation notation, and we have the general form of the explicit formula for a geometric sequence, a times the ratio to the k minus 1. And we start at k equals 1, but we go to infinity. So when you plug in k equals 1 first into this, you get a times r to the 0, which is just going to be a. When you plug in k equals 2, you're going to get a times r to the 1, or just ar. When you plug in k equals 3, etc., where you get ar squared. And this sum goes forever. These three dots indicate that the sum does not end. This is called a series when the sum is infinite infinitely long, is called a series. And a geometric series if it's the sum of the terms of a geometric sequence. Now, find the sum of each series if possible. Let's explore some of these. So we have a half plus a fourth plus an eighth plus a 16th plus etc. This would go forever. It's possible to know what this sum is without any formulas. If we start with a whole, for example, let's draw a whole circle. And then I cut that whole circle. So let's say this has an area of 1 square unit. And we cut that circle in half. Then the area of 1/2 of it will be a half a square unit. Now the other half, let's cut in half as well. And so here would be a quarter. Let's take the remaining quarter and cut it in half, giving us a 1/8 right here. Take the remaining 1/8 and cut it in half, giving us a 1/16 in there, etc. This could continue, squeezing in this gap right here, more and more infinitely many slivers of this circle. And there's going to be, it's possible in theory to do this so that there's infinitely many pie pieces. And notice that if you take all these pie pieces and put them back together, you should get the one whole circle again. So it stands to reason that the sum here should be just 1, representing the entire circle. Let me shrink that down a little bit, put that right there. Okay, the next one. 0.3 plus 0.03 plus 0.003, etc. forever. Well, this is just going to be 0.3 plus 0.03 puts a 3 there, plus 0.003 puts a 3 there. These 3's are just going to repeat forever. And we already know that this sum is equal to 1/3. 0.3 repeating is 1/3. So we've seen 2 cases now where it is possible to add infinitely many things together and get a finite sum back. We've done it twice. Infinitely many things added together get a finite number back. And of course it's possible when you think of it the other way. If you take 1, it's possible to break it apart into infinitely many pieces, similar to like we did right here with the circle. So any finite number could be broken up into infinitely many pieces in a similar process. So it's certainly possible for an infinite series, or a series is always infinite, for a series to have a finite sum. Look at this last example over here. 1 plus 2 plus 4 plus 8. This is a geometric series. I do want to point out these series are all geometric. Look at the first one here. Right, to go from term to term, we are multiplying by 1/2. Right, that's true as we go from term to term. We just keep multiplying by 1/2. In this one here, we keep multiplying by 1/10. Right, to go from 0.3 to 0.03, we multiply by 1/10. Multiply by 1/10 again to go from 0.03 to 0.003. That pattern continues. Here, to go from 1 to 2, we multiply by 2, and we multiply by 2 again, and we multiply. So we do see that all of these are in fact geometric series because they are adding up the terms of a geometric sequence. But in this last case, 1 plus 2 plus 4 plus 8, the number we keep adding keeps getting larger and larger. And so we're going to start seeing some infinities or near infinities down here at the end. And when you add them all up, you're obviously going to get infinity. This series has no sum. Or we can say it's equal to infinity, or we can say it does not exist. There is no finite number that this series adds to. Okay, and so the question is going to be which geometric series have sums and which geometric series do not. If a geometric series, or if any series has a sum, we say it's a convergent series. And if a series does not have a sum, we say it's a divergent series. And for the case of geometric series, the deciding factor is going to be the size of the ratio. If the ratio is between -1 and 1, not inclusive, so it can't be 1 or more than 1, and it can't be -1 or less than -1. So it has to be strictly in between -1 and 1. Then a geometric series is convergent, meaning it has a sum. Otherwise, the series is divergent, meaning it has no sum. Furthermore, the sum of a convergent series is given below. I should say convergent geometric series there is given below. So we have the geometric series written out, a plus ar squared plus ar cubed, etc. forever to infinity. It will equal a divided by 1 minus r, where a is the first term, and of course r is the ratio. So in words, you would say the sum of a convergent geometric series is the first term divided by 1 minus the ratio. And of course, this is only true if the ratio is between -1 and 1. Otherwise, you will say that the series here is divergent, has no sum. Now this formula comes from the formula for the, let me back up here to right here. If the ratio, if r is between -1 and 1, so it'd be like a fraction. So imagine a 1/3, a 1/2, a -3/4, any of those fractions that are between -1 and 1. And we want to include more and more terms. In fact, we want to include infinity terms. So we're going to let n approach infinity. So this n right here in the formula will approach infinity. And if you have a number, say 1/2, and you raise it to a larger and larger power, this part here will shrink to 0. 1/2 to the 50th power is effectively 0. 1/2 to the 100th power is effectively 0, even closer to 0. And so that part there approaches 0, leaving just 1 times a, which is a, all over 1 minus r. So this is where we get the a over 1 minus r formula when n approaches infinity, when the ratio is the appropriate size. Okay, we're going to show that this formula confirms our answers above. So we know that the answer above, we know that the first term is 1/2, and the ratio is 1/2. And the ratio is between -1 and 1. Check. You always want to make sure the ratio is the correct size. So our answer should be the first term divided by 1 minus the ratio. Well, the first term is 1/2, and the ratio is 1/2. So we get 1/2 divided by 1/2, and that confirms the 1. In this middle case, the first term, a, is 3/10. I'll write it in fraction form. 0.3 is 3/10, and the ratio is 1/10. Oops. And 1/10 is between -1 and 1. Check. So the answer to this should be first term, a over 1 minus r, and I'm saying the answer up here should be a over 1 minus r, and that should give us, first term is 3/10 over 1 minus r over 1 minus 1/10, that's 9/10, so we get 3/10 over 9/10. Invert and multiply, the 10s will cancel, so we get 3/9, and 3/9 is the same thing as 1/3. So we confirm the 1/3 using the formula. And over here, of course, you would say the a is a 1, but the ratio is 2, and 2 is not in the interval from -1 to 1, so you can say it this way. 2 is not an element of this interval. We need the ratio to be between -1 and 1, and 2 is not, so we say that this series diverges. Series diverges. Okay, last slide. Find the indicated sums if possible. So we have a sum from k equals 0 to k equals 12. So this is a finite number of terms being added, so it's not a series. The next one will be a series. Look at that infinity up top. This third one here is also a series because the pluses or the dots go forever. But this last one is not a series because we have a final ending term. So this is a finite number of terms added together, so the answer will be finite. This is a finite number of terms added together, so that answer will be finite. And these ones are series. And the series will only be finite, will have a finite sum if the ratio is of an appropriate size. So let's just do these one at a time. This one here, so if you plug in k equals 0, plug k equals 0 into this expression, we get, do the exponential part first, k is 0, so we just get 2 to the 1, which is 2, and then times 3, so we get 6. Plus, now plug in k equals 1. K equals 1, we're going to get a 2 squared here, which is 4 times 3, and 4 times 3 is 12. Plus, the next one's going to be 24. I'll leave it to you to verify that. When k is 2, we get that 24. And we keep this up until we get to the final one. And the final one will be when k is 12. So you plug into 12 for k, we're going to get 3 times 2 to the 13th, which I won't calculate. I'll just write 3.2 to the 13th. And this is where the sum stops. Okay, so this is a geometric. You can clearly see we're doubling to go from term to term. That's simply because as k increases, we just keep getting larger and larger powers on 2. So to go from term to term, we just double the previous term to get the next term. Right? You can see that clear geometric pattern when you start writing out some of the terms. Multiply by 2, multiply by 2. You can always recognize a geometric summand by there will be some sort of constant to some sort of number raised to a k plus or minus some number. So this is basically an exponential function here with a base of 2. And that base of 2 is going to indicate what the ratio is, multiplying by 2 to go from term to term. So that's important to discover what the ratio is. And for partial sums, we need to also know how many terms there are. So we got to determine how many terms we have here. And if you recall, the way to do that is to do final value minus initial value plus 1. So we do 12 minus 0, which is 0, add 1 is 13. So there's 13 terms. So that's the n in our formula. The a is the first term, the a is the 6, and the r is the 2. So the fact that we're doubling by 2 is our r. These are all the different components you need to apply the formula, because the formula is first term times, now the ratio is 2, so I'm going to go with the version of the formula that has the r's first. So it's r to the n minus 1 over r minus 1. And we know all three of these numbers now. A is the first term, so a is 6. The ratio is 2, and the n is 13. So we have 2 to the 13th minus 1 over 2 minus 1. And I'm not going to go ahead and reach for the calculator, but I will do some of the simplification. 2 minus 1 is 1, and 6 divided by 1 is just 6. So that denominator we don't need to write, and we could just say we'll stop here as an answer. So here's the sum of the first 13 terms of this geometric series. Next one. Sorry, I said this is not a geometric series. This is what's called a geometric partial sum. It's a sum of 13 of the terms of a geometric sequence. This here is a geometric series. And it's important that you don't confuse the word series and sequence. Sequence is a list of infinitely many numbers, and a series is a sum of those infinitely many numbers. And they don't have the same meaning. So I'll try to be careful in my language, as should you. But what I have circled right now is a geometric series. And I starts at 2, so we're going to plug in 2 first. So we do 2 minus 2, that's going to be a 0. 0.9 to the 0 is just 1. So our first term is going to be 3 here. When I is 3, now we plug in 3. So we're going to get 3 times 0.9. And then the next one will be 3 times 0.9 squared, etc. And this will go forever. It does not end. This is certainly enough to see that we have a geometric, right? We're multiplying by 0.9, right, to go from term to term. So the 0.9 is our ratio, and the first term is 3. Be careful you don't just assume that what you see in here reveals the first term easily. You need to plug in your starting value of I into this. That will reveal what the first term of your sum actually is. If this had been starting at I equals 3, then our first term would have been this one. This would have been A, and not 3. So be careful about that. Always make sure you plug in your first I into your summand. That will dictate what your first term is. And since this is a series, all we have to do is determine whether the r is between -1 and 1. Well, 0.9 is. So this is an element of the interval from -1 to 1. Check. So because our ratio is at an appropriate size, we know that this series will have a sum. It's going to be equal to a divided by 1 minus r. That's the same formula that we have for this, but reverse the subtraction and then let that part go to 0. Or just make this part be 0 and we get this formula. And if that part is 0, then we have a -1 times a. So we have a negative a over an r minus 1, and that negative can distribute down here instead and just say positive a over 1 minus r, which is generally what's used for the sum of a series if it's convergent. And all we need to know is a and r, which we do. A is the first term, and the ratio is 0.9. So we have 1 minus 0.9. 1 minus 0.9 is 0.1. So we have 3 over 0.1. And so this is going to give us 30 is the sum. Now, if you do a sum of the first 1,000 terms, you're going to get an answer close to 30. But when you do a sum of the first 1,000,000 terms, you'll get even closer to 30. But a sum of all the terms, infinitely many, you will get 30. Right? This is not a wavy equal sign. This is an equal to 30. In the same sense that up here, that we don't get approximately 1, because when you take all infinitely many pieces and put them back together, you get 1. But if you stop the process, leaving a tiny little sliver that's empty still, then you'll get close to 1. But if you don't stop the process and you add up all of them, all the pieces put back together give you exactly 1. So just be careful that when we use the formula for a series, that this is an equal sign, not an approximate sign. Okay, the next one, we have 2 minus 8/3 plus 32/9 minus 8/3 plus etc. Let's see if this is geometric or not. It's certainly a series because the dots go forever. But to go from 2 to -8/3, well, we just take -8/3 and divide it by 2. That's how we figure out the common ratio. And in fact, that's why it's called a ratio, because you take any one term and divide it by the prior term, you get the same number always. And so -8/3 divided by 2 is -4/3. So let's double check that we multiply by -4/3 to go from term to term. Let's make that not look like x minus, but multiply by -4/3. Is that true to go from here to here? Well, negative 8/3 times negative 4/3 is positive 32/9, so check. And to go from here to here, positive 32/9 times negative 4/3. Ooh, this is a typo. This is a mistake. That should not be that number. So it should be subtract 128, and then 9 times 3 is 27. That's what should be written right there. And if that was written right there, then this would be the indication of a geometric series. Okay, so let's go with that assumption. And we get, well, the ratio is negative 4/3. Well, negative 4/3 is negative 1.3 repeating. And that's not in the interval from negative 1 to 1. It's left of negative 1 on the number line. So therefore, we can say right away that this series is divergent. So since the ratio negative 4/3 is not in the interval from negative 1 to 1, then the series diverges. Or we can say it's divergent. It has no sum. Okay, and then the final one, this is a partial sum because it ends. The question is going to be, is it geometric? The answer is, it appears to be. It looks like we're just multiplying by 3, right, to go from term to term. And assuming that happens, we're going to have to figure out at what point do we get to this number right here. So we're going to have to figure out what number term this is, so we know how many terms there are here. So we're going to use the explicit formula to do this. A sub n is equal to a times r to the n minus 1. We know the ratio, and we know the first term is 2. And so we plug in this 39366 is the output, and we want this to be 2 times 3 to the n minus 1. And we just have to figure out what n will take care of this for us. So we're going to divide both sides by 2. 19683 is equal to 3 to the n minus 1. Now I can convert this to a log form, which will be helpful. So this tells us that log base 3 of 19683 should equal n minus 1. And I reach for the calculator, and I do this logarithm, log base 3 of 19683, and that gives us 9. We expected a whole number here because our answer should be a whole number, and then add 1 to both sides, and we have n is 10. So this is the 10th term. By this, I mean the final number is the 10th term. So let's indicate that. This is our first term, this is our second term, this was our third term, and we've just determined that this is the 10th term in this sequence. And that's all I really needed to know, because that means the n will be 10, and the r is 3, and the a is 2. And the formula for such a sum, since the ratio is 3, I'm going to do the version where I have the r's first. So we have a times r to the n minus 1 over r minus 1. And the first term is 2. The ratio is 3, and the number of terms is 10. And this becomes a 2, which cancels with that 2. That's nice. And so we really just get 3 to the 10 minus 1. 59,048 will be the sum of these 10 terms. That concludes our lesson on geometric sequences and series.